Hello students, let us discuss about the new unit. Name of this is Series Solutions of Ordinary Differential Equations. First of all, we should know why we study this. So in previous unit, we had discussed about the higher order ordinary differential equations with constant coefficients, and for variable coefficients, the method Euler-Cauchy method. That method can be used only for special type of variable differential equations, but we may have different types of differential equations with variable coefficients. So solution of this type of differential equation may not possible using that method. In this unit, we discuss about the series solution of ordinary differential equation with variable coefficient. Now the question is, why this is called series solution, right? Name of the unit is series solution of linear differential equation. So why it is called series solution? We say that because when we solve the variable differential equation, then we will get our answer or our solution in the form of infinite series. In this unit, we will discuss about the power series method. Let us look definition of power series, which is defined as an infinite series of the form summation n running from 0 to infinity or summation k running from 0 to infinity ak x minus x0 raised to k. If we expand this, that means if we put different values of k, we can write a0 plus a1 x minus x0 plus a2 x minus x0 square plus and so on. So this series is called power series in powers of x minus x0, because in each and every term we have different powers of x minus x0. Okay. Here a0, a1, a2, a3 and so on, all are constants. They are called coefficients of the series, and x is variable. Also x0 is a constant, which is the center of series. Okay. If we put x0 is equal to 0, then our series will be in the form summation k equal to 0 to infinity ak x raised to k. If we expand this, we will get a0 plus a1x plus a2x square plus and so on. We say that this is power series in powers of x. Now let us look for some standard power series. We have already discussed this in the previous semester. We can say these are series of standard functions. Particularly these series are Maclaurin series. Now to find power series method, we should know about the classification of singularities. That means there are different types of point like ordinary point, singular point, regular singular point, irregular singular points. We can find power series about ordinary point, and the another method, that is Frobenius method, we can find series of using this method for regular singular point. So we should know about this singularity first. So for that, consider the second order homogeneous ordinary differential equation with variable coefficient as p0x d square y by dx square plus p1x dy by dx plus p2x y is equal to 0. Here p0x, p1x and p2x are the polynomials, or we can say they are coefficients which are having variables, that means variable coefficients. Okay. Assume that the coefficient of d square y upon dx square is not equal to 0. Why this? Because if p0x is 0, then our differential equation will be of order 1. Okay. So let us assume p0x not equal to 0. Okay. Divide this equation 1 by p0x. So we get d square y by dx square plus p1x upon p0x into dy by dx plus p2x upon p0x into y is equal to 0. Let us say p1x upon p0x is capital P of x and p2x upon p0x is capital Q of x. Okay. So our differential equation becomes d square y upon dx square plus p of x into dy by dx plus q of x into y is equal to 0. This form is called standard form or normal form or canonical form of this equation number 1. Okay. So the power series solution of this standard form or standard equation about a point x0 depends on the following definition. So these are some basic definitions. First we discuss about the ordinary point. A point x0 is said to be an ordinary point or regular point if both p of x and q of x are analytic at x0. Analytic means it must be differentiable at that point. Or we can say both p of x and q of x have Taylor series around x equal to x0. Also we can say if p0x is not equal to 0 at x equal to x0, then x0 is an ordinary point. So from any of these three sentences you can find ordinary point. Second is about the singular point. If the point x0 is not an ordinary point, then it is said to be singular point. See, in previous one we had discussed about p0x not equal to 0, then that point is ordinary point. Here p0x equal to 0, then the point is singular point. That means the point which is ordinary is not singular, and then the point which is not ordinary is singular. Or we can define singular point like a point x0 is said to be singular point of equation 2 if either p of x or q of x or both are not analytic at x0, that means not differentiable at x0. Now the other two definitions are depend on the second one. That means if the point is singular point, then only we check that point is whether regular singular or irregular singular. Okay, so first let us discuss about regular singular point. So a singular point, the point must be singular, right? A singular point x0 is called regular singular point if both functions x minus x0 p of x and x minus x0 square q of x are analytic at x0. Second one, irregular singular point. A singular point x0 is said to be an irregular singular point if either x minus x0 p of x or x minus x0 square q of x or both are not analytic at x0. Okay. So are you all clear about this? There are main 4 points: ordinary point, singular point, If the point is singular, then we will discuss that point whether it is regular singular or irregular singular. Okay. Let us discuss about the example. Okay. The question is, for the following differential equations, discuss about ordinary point, singular point, regular singular point and irregular singular point. Or we can say discuss the singularity for the following differential equations. Okay. Consider the first one, y double dash plus x cube plus x square plus 2 into y dash minus 5 into x square minus 4x minus 2 into y is equal to 0. Okay. Let us first find p0x, p1x and p2x. They are the coefficients. p0x is coefficient of y double dash, it is 1. Then coefficient of y dash, we say that as p1x. So p1x is x cube plus x square plus 2. And the coefficient of y, we say that as p2x. So it is minus 5 into x square minus 4x minus 2. From this we can write p of x and q of x. So our p of x is x cube plus x square plus 2 divided by 1 and q of x is minus 5 x square minus 4x minus 2 divided by 1. Okay. Here note that p0x is not equal to 0 for all points of the set of real numbers R. That means here denominator of p of x and q of x is not equal to 0 for all the points of R. Right? So we can say p of x and q of x both are analytic at each and every points of R. If p of x and q of x both are analytic, then all points are ordinary point. Right? So our answer is all points of the set R are ordinary points. Since all are ordinary points, we don't have any singular point. So note that here there is no singular point. There is no singular point, so we will not check about the regular singular point and irregular singular point. Let us discuss the second example. Here the coefficient of y double dash, that means p0x is x cube into x minus 1, p1x is 3 into x minus 1 and p2x is 7x. So our p of x, that means p1x divided by p0x is nothing but 3 upon x cube and q of x is equal to p2x upon p0x, that is nothing but 7x upon x cube into x minus 1. Okay. Now here we have in the denominator of px there is x cube, in the denominator of qx x cube into x minus 1. Okay. See, if we put x equal to 0 in p of x, then its denominator will become 0. So p of x will be infinity. So we cannot find its derivative. That means it is not differentiable. It is not differentiable. That means we can say it is not analytic. So if we put x equal to 0, p of x is not analytic. Therefore, we can say, okay, at x equal to 0, p of x is not analytic. Now let us check q of x. So in q of x, if we put x equal to 0 or if we put x equal to 1, in both cases denominator of q of x will become 0. Again, if denominator will become 0, q of x is not analytic. Right? So if we talk about both p of x and q of x, we are getting 2 points. x equal to 0 and x equal to 1, at which our two functions p of x and q of x are not analytic. So if p of x and q of x are not analytic, we can say that two points are singular points. Okay, so we have x equal to 0 and x equal to 1 are singular points. Okay, so these two are singular points. So except these 2 points, all the points of set R are ordinary points. So we can write R minus 0, 1 are ordinary points of the given differential equation. Now we have two singular points, so we need to check whether these 2 points are regular singular or irregular singular. Let us check the first point, x equal to 0. So for this we need to check whether x minus x0 p of x and x minus x0 square q of x are analytic or not. Okay, so we want to check at x equal to 0, so we put x0 is equal to 0 here. So x minus x0 p of x is 3 upon x square and x minus x0 square q of x is 7 upon x minus 1. Now observe that x minus x0 p of x is not analytic at x equal to 0 because in the denominator of that there is x. If we put x equal to 0, it will becomes infinity. P of x minus x0 p of x becomes infinity. That means it is not analytic. Okay. Thus x equal to 0 is an irregular singular point. Again, it is not analytic, not regular, that's why it is called irregular singular point. Let us check for the point x equal to 1. So for x equal to 1, x minus x0 p of x, we get 3 into x minus 1 upon x cube, and x minus x0 square q of x is 7x into x minus 1 upon x cube. Now since we are checking for x equal to 1 point, so put x equal to 1 in both x minus x0 p of x and x minus x0 square q of x. So see, if we put x equal to 1, so there is no problem with the denominator. Denominator will not become 0, right? So for x equal to 1, both x minus x0 p of x and x minus x0 square q of x are analytic, right? Analytic, that means regular. It was first singular point, now it become regular for x minus x0 p of x and x minus x0 square q of x. That's why we say x equal to 1 is a regular singular point. Okay. I think you all are clear about this ordinary point, singular point, regular singular point and irregular singular point. Again, let us discuss about the third example. Here p0x is 1 minus x square, p1x is minus 2x, p2x is n into n plus 1, right? So p of x is minus 2x upon 1 minus x, 1 plus x, q of x is n plus 1 divided by 1 minus x, 1 plus x. Clearly, if we put x equal to 1 and x equal to minus 1, both p of x and q of x are not analytic. Therefore, we can say x equal to 1 and minus 1 are singular points of given differential equation, and r minus 1, 1 are ordinary points. Now, though x equal to 1 and minus 1 are singular points, we check whether they are regular singular point or irregular singular point. So for x equal to 1, let us check x minus x0 p of x. It is 2x upon 1 plus x. And x minus x0 square q of x, it is n plus 1 divided by minus 1 plus x. Now observe that if we put x equal to 1 in x minus x0 square q of x and x minus x0 p of x, then both functions are analytic. So we can say x equal to 1 is regular singular point. And let us check for x equal to minus 1. So x minus x0 p of x is minus 2x upon 1 minus x, and x minus x0 square q of x is x plus 1 n into n plus 1 divided by 1 minus x. Now if we put x equal to minus 1 in x minus x0 p of x and x minus x0 square q of x, then both functions are analytic. So again x equal to minus 1 is regular singular point. Okay. So next, the series solution about an ordinary point we will discuss in the next lecture. Thank you.